After studying this module, you shall be able to comprehend the need for modification in the Debye-Hückel theory, understand the finite size model, learn the experimental methods to determine mean activity coefficient. The Debye-Hückel theory proposed by Peter Debye and Erich Huckel is only applicable to strong electrolytes. Strong electrolytes are completely dissociated into ions when the parent salt is dissolved in water. There exist ion-ion interactions in the solution. In order to measure these ion-ion interactions, we need to study in detail about these interactions. Let us recapitulate the Debye-Hückel theory. In an electrolytic solution, ion-ion interactions are bound to operate. Further, the chemical potential change delta mu II in going from a hypothetical state of non-interacting ions, that is a discharged state, to a state in which the ions of species I interact with the ionic solution, that is the charged state, was considered as a quantitative measure of these interactions. We also arbitrarily choose a reference ion, that is the central ion, from the assembly of ions. From the postulates of Debye-Hückel theory, these ion-ion interactions are assumed to be purely Coulombic in origin. Hence, the chemical potential change arising from the interaction of species I with the electrolytic solution is Avogadro's number Na times the electrostatic work W, resulting from taking a discharged reference ion and charging it up in the solution to its final charge. Mathematically, this is given by equation 1 as delta mu II equals to Na times W. Further, we need to obtain the electrostatic potential at the surface of the reference ion. In order to obtain the theoretical expression for the potential psi reference ion, we need to understand the distribution of ions around a given reference ion. Debye-Hückel model treats only ion, that is the central or the reference ion, as a discrete charge, while the remaining ions in the solution are being smoothed out to give a continuous charge density. As a result, the negatively charged ions have a tendency to accumulate near a positive ion, while the positively charged ion accumulates near a negative ion. Therefore, the smoothed out positive and negative charge densities do not cancel out, but rather this imbalance gives rise to an excess local charge density rho r. The local charge density rho r fades off as the distance from the central ion is increased and thus dies away towards zero. Thus, the problem of calculating the distribution of ions in an electrolytic solution reduces to the calculation of the variation of excess charge density rho r with distance r from the central ion. The mean distribution of positively and negatively charged ions is spherically symmetrical. Thus, the excess charge density rho r was considered to be given by two equations. Number 1 is the Poisson equation in spherical polar coordinates as given by equation 2, that is rho r is equals to epsilon by 4 pi into 1 by r square into d by dr of r square d psi r by dr. Number 2 is the linearized Boltzmann distribution law as shown by equation 3 as rho r equals to minus summation ni naught zi square E naught square psi r divided by kt. We equate these two expressions 2 and 3 for the excess charge density and we get the fundamental partial differential equation of the Debye-Hückel model, that is the linearized Poisson-Boltzmann equation, that is the equation 4 given as 1 by r square into d by dr of r square d psi r by dr equals to chi square psi r, where chi square is equal to 4 pi by epsilon kt into summation of ni naught zi square E naught square. We assume that ions can be treated as point charges. Therefore, based on this assumption, the solution of the linearized PB, that is the Poisson-Boltzmann equation, turns out to be psi r equals to Zi E naught e to the power minus chi r divided by epsilon times r. This is our equation 6. This expression 6, which relates the variation of the excess charge density with distance around the central ion or the reference ion, also yields a simple physical picture. We consider a positive reference ion surrounded by a cloud of negative charges of radius chi inverse, that is the Debye-Hückel length. The charge density in this ionic atmosphere or the ionic cloud decays. According to equation 6, thus the interaction between a reference ion can be considered to be equivalent to the interactions between the reference ion and the ion cloud. Hence, the central ion sets up a potential psi cloud that is equal to minus Zi E naught by epsilon chi inverse. This is our equation 7. In other words, the charging work can be obtained by integrating the potential at ionic cloud, psi cloud, from a state of zero charge to a state of full charge Zi E naught, and W is equals to minus Zi square E naught square chi divided by 2 epsilon. Thus, the energy of these interactions is given by equation 9 as delta mu I equals to minus Zi square E naught square chi Na divided by 2 epsilon. These predictions were checked using the empirical treatment of ionic solutions. In solutions of non-interacting particles, the chemical potential change in going from a solution of unit concentration to one of the concentration Xi is given by equation 10 as mu I minus mu I naught is equals to RT ln Xi. While on the other hand, in case of electrolytic solutions where ion-ion interactions are present, it is experimentally observed that mu I minus mu I naught is not equals to RT ln Xi. Let this be our equation 11. Thus, for electrolytic solutions, we use new terms, that is activity AI and activity coefficient gamma I, where AI is equals to gamma I into M. This is our equation 12. Therefore, the change in chemical potential can be related to activity by delta mu II equals to RT ln AI or delta mu II equals to RT ln gamma I. Gamma I accounts for the interaction of the charges. Thus, from the equation 9 and 14, we have RT ln gamma I equals to delta mu II equals to minus Na into Zi E naught square divided by 2 epsilon chi inverse as our equation 15, which is the Debye-Hückel expression for the experimentally inaccessible individual ionic activity coefficient. This expression is transformed into the Debye-Hückel limiting law, which determines the experimentally measurable quantity, that is the mean ionic activity coefficient. That is log gamma plus minus is equals to minus A into Z plus Z minus into root I. This is our equation 16, where A equals to 1 upon 2.303 into Na E naught square B divided by 2 epsilon RT, and B is given by 8 pi Na E naught square upon 1000 epsilon KT whole to the power 1 by 2. I is the ionic strength equals to half summation Ci Zi square. Equation 16 indicates that the logarithm of the mean activity coefficient falls linearly with the square root of the ionic strength I. The Debye-Hückel limiting law was seen to be valid with experimental values of the activity coefficient at extremely low electrolyte concentrations, while the law failed at high concentrations. Moreover, there should be an increase in gamma plus minus with increase in the concentration, whereas the Debye-Hückel law indicated a continued decrease. Thus, there an improvement of the theory was required. Let us see the modification in the Debye-Hückel law. In order to improve the Debye-Hückel theory and make it valid at higher concentrations, we first need to focus on the assumptions we made at the beginning of this theory. Further, for the derivation of the Debye-Hückel limiting law, we had considered ions as point charges. The question arises that is it reasonable to consider ions as point charges? The answer to this question depends on Debye-Hückel length chi inverse. The mean thickness chi inverse of the ionic cloud depends on the concentration. Mathematically, chi inverse is equals to epsilon kT divided by 4 pi summation over I Ni naught Zi naught E naught square whole to the power 1 by 2. This is our equation 17. Therefore, on increasing the concentration of electrolyte, the mean thickness of ionic cloud chi inverse decreases, whereas at low concentration, the radius of the ionic cloud is 100 times the radius of the ion. In other words, at a very low concentration or for a low value of Ni naught, the charge cloud is diffused. Hence, with respect to a large ionic cloud, the reference or the central ion can be treated as a point charge. Thus, the results from Debye-Hückel theory are in accordance with experimental results. On the other hand, at higher concentration, it is only 10 times. Since at higher concentration, ionic cloud will be concentrated around the reference ion, therefore, under these circumstances, the reference or the central ion cannot be considered as a geometrical point charge. Thus, more concentrated the solution, the smaller is the size of the ionic cloud chi inverse, and the concept of point charge approximation becomes less valid. In order to make the theory applicable at higher concentrations, the concept of finite size of ions must be introduced into the mathematical formulation. In order to remove the assumption that ions can be treated as point charges, it is necessary at first to recall at what stage in the derivation of the theory the assumption was invoked. The linearized Poisson-Boltzmann equation involved neither the point charge approximation nor any considerations of the dimensions of the ions. Hence, the basic differential equation 1 by r square d by dr into r square d psi r by dr gives chi square psi r, the equation 18, and its general solution, that is psi r equals to a into e to the power minus chi r by r plus b into e to the power plus chi r by r. The equation 19 can be taken as a basis for generalization of the theory for finite sized ions. The integration constant B is evaluated through boundary conditions. The thermal forces completely dominate the Coulombic forces. When far enough from the central ion, situated at r equals to 0 and their electroneutrality, that is the electrostatic potential psi r, vanishes at distances sufficiently far from such an ion. That is, psi r approaches 0 as r approaches infinity. Moreover, if B had a finite value, then equation 19 shows that the electrostatic potential would shoot up to infinity. That is, psi r approaches 0 as r approaches infinity. The statements are contradictory. In order to remove this, and the first condition will be satisfied only if B equals to 0. Hence, equation 19 reduces to psi r equals to a into e to the power minus chi r by r. This is our equation 20. The charge dq in any particular spherical shell of thickness dr situated at a distance r from the origin is given as dq equals to rho r into 4 pi r square dr. The charge density rho r is obtained as given by equation 21. Using equation 20 in 21, we get equation 22 as rho r equals to epsilon by 4 pi into chi square into a into e to the power minus chi r by r. Thus, by combining the equations 20 and 22, we get dq equals to minus a chi square epsilon into e to the power minus chi r times r into dr as our equation 23. The total charge in the ionic cloud Q cloud is equal to minus Zi E naught as required by the electroneutrality condition, and on the other hand the result of the integrating dq. Thus we get Q cloud is equals to minus Zi E naught equals to integration from a lower limit to infinity dq dr equals to minus a chi square epsilon integration from lower limit to infinity of e to the power minus chi r times r into dr as our equation 24. The lower limit used for the integration needs to be investigated. If the point charge model, we used a lower limit of 0. It implies that the ion cloud commences from 0, that is from the surface of a 0 radius ion, and extends up to infinity. But in this present case, since the ions are considered to be of the finite size, hence a lower limit of 0 is not acceptable. The lower limit should be a distance corresponding to the distance from the center of the ion at which the ionic atmosphere commences. This is shown in figure where for a finite sized ion, the ion atmosphere starts at a distance a from the center of the reference ion. Thus, for the lower limit of integration, we use a distance parameter which is greater than 0. Symbol A be used for the ion size parameter. Thus, equation 24 transforms to equation 25. Using integration by parts to solve the integral, we get the equation 26. Hence, inserting equation 26 in equation 25, we get equation 27. Hence, we get A equals to Zi E naught by epsilon into e to the power chi a divided by 1 plus chi a as our equation 28. Using this value of A in equation 20, we obtain a new and less approximate expression for the potential psi r at a distance r from a finite sized central ion. Psi r equals to Zi E naught by epsilon into e to the power chi a divided by 1 plus chi a into e to the power minus chi r by r as our equation 29. Now we shall see the theoretical mean ionic activity coefficient in the case of ionic clouds with finite sized ions. In order to obtain the ionic atmosphere contribution psi cloud to the potential psi r at a distance r from the central ion, we utilize the concept of the law of superposition of potentials. Thus, we get psi cloud equals to psi r minus psi ion. Substituting the value of psi r and psi ion, we get psi cloud equals to Zi E naught by epsilon r into e to the power chi into a minus r upon 1 plus chi a minus Zi E naught by epsilon r, which can be further written as equation 30. In order to calculate the activity coefficient from the expressions RT ln gamma I equals to delta mu I as our equation 14 and delta mu I equals to Na Zi E naught by 2RT times psi, that is from ln gamma I equals to Na into Zi E naught by 2RT times psi as the equation 31. It is necessary to know psi, which is the potential at the surface of the ion due to the surrounding ions, that is due to the cloud. Since in the finite ion size model, the ion is taken to have a size A, it means that psi is the value of psi cloud at r equals to A. This is our equation 32. The value of psi cloud at r equals to A is flourished by setting r equals to A in equation 30. Hence, we get equation 33 as, by substitution of the expression 33 for psi equals to psi cloud at r equals to A in equation 31, we get equation 34. This individual ionic activity coefficient can be transformed into mean ionic activity coefficient through the same procedures as for the Debye-Hückel limiting law. Hence, the expression for log gamma plus minus in the finite ion size model is the Debye-Hückel limiting law, that is log gamma plus minus equals to minus a mod z plus z minus into root I as our equation 35. Or we can have log gamma plus minus equals to minus a into z plus z minus root I divided by 1 plus chi a as our equation 36. Here a is referred as the ion size parameter. Note that the ion size parameter has the dimensions of meters. Thus, we have log gamma plus minus equals to minus a into mod z plus z minus into root I into 1 plus chi a inverse, which is further equals to minus a into mod z plus z minus into root I into 1 minus chi a. Expanding it using the binomial series and using only the first two terms, we get equation 37. Or this can be written in the form of equation 38 as log gamma plus minus equals to minus a into mod z plus z minus into root I plus constant into root I. It was seen that the plot of log gamma plus minus versus root I curve gives the value of log gamma plus minus higher than those given by the limiting law. The deviation increases with the concentration. Moreover, the general shape of the predicted curve that is given in a figure is in the right lines. Further, in equation 38, the first term explains the decrease of log gamma plus minus with the square root of ionic strength, while the second term explains the occurrence of the positive slope or the increase in chi. Further, the first term dominates at lower concentration and the second term dominates at higher concentrations. Figure shows the comparison of the experimental mean ionic activity coefficients. Now, having a look at the experimental determination of mean activity coefficient. In very dilute solutions of electrolytes, the ions are surrounded only by water molecules. Interionic and ion-solvent interactions are negligible, hence the solution behaves ideally. When the concentration of ions in the solution is greater than approximately 0.01 molar, a shielding effect arises around the ions. That is, the cations tend to surround the nearby anions and the anions tend to surround the nearby cations. These interactions make the solution non-ideal, and therefore we need to define activities for cations and anions A plus and A minus separately. The difference between activity and other measures of composition arises because molecules in non-ideal solutions interact with each other, which give rise to activity coefficient gamma plus and gamma minus. When there is ion-ion interaction, effective concentration decreases, that is, the activity will decrease. Similarly, when ion-solvent interactions exist, some of the solvent molecules become separated from the bulk solution. Therefore, both effective concentration and activity increases. There are several methods for the determination of activity coefficients. Now, looking at the determination of gamma plus minus from solubility product. When a substance mixes with another substance to form a homogeneous mixture, a true solution is formed. The substance that is present in greater amount is called the solvent and the other substance is called the solute. The solubility of a solid in a liquid is governed by many factors like the nature of the solute, nature of the solvent, temperature, pressure, concentration of the solute, presence of other solutes, etc. The maximum amount of solute that can dissolve in a fixed quantity of the solvent at a given temperature and pressure is called saturated solution. An ionic solid exists in the solid state as negative and positive ions packed into a regular three-dimensional array called crystal lattice. The electronic interaction between the oppositely charged ions, the crystal lattice, together. The energy required to disband the ions from the lattice is called the lattice energy of the ionic solid. For an ionic solid to dissolve in a solvent, the solvent has to overcome the attractive forces between the ions. This energy supplied by the solvent to overcome the forces of attraction between the ions is called solvation energy. When the solvent involved is water, this energy is called hydration energy. When the solvent energy exceeds the lattice energy, the lattice breaks up and the individual ions drift into the solution. If the concentration of the ions is very low, they drift far apart from each other and there is virtually no interaction amongst them. Such a solution is called an ideal dilute solution. However, if the concentration of the ions is high, that is more than 10 to the power minus 3 molar, the ions are forced close together. The electron clouds of the adjacent ions interact with each other, leading to deviation from ideality. The effective concentration of the ions in solution is no longer equal to the actual concentration. The effective concentration of ion in solution is known as its activity. The ratio of the activity of an ion to its actual concentration is called as the activity coefficient. If the concentration of an ion is expressed in terms of its molality, that is the moles of ion per kilogram of the solvent, then its activity can be defined as A equals to gamma m. Equation 39, where gamma is the activity coefficient and m is the molality. Activity coefficient of individual ions can never be determined because in a strong electrolytic solution, only cations and only anions can never exist. Cations are always accompanied by anions and vice versa. Therefore, gamma plus and gamma minus cannot be determined individually, so we define a new term, mean activity coefficient, which is represented as gamma plus minus. The mean activity coefficient gamma plus minus is a measure of ion-ion interactions in solution. Mathematically, it is given as gamma plus minus equals to gamma plus to the power x, gamma minus to the power y raised to power 1 upon x plus y as our equation 40, where gamma plus and gamma minus are the activity coefficient of the cation and anion respectively. Now looking at the solubility product, when the solution energy supplied by the solvent is capable to overcome the lattice energy of an ionic solid, the solid remains practically undissolved. Such a salt is called spherically soluble salt in that solvent. A spherically soluble salt dissolves to such a small extent that it always forms a saturated solution. A dynamic equilibrium exists between the undissolved salt in the solid state and its dissociated ions in the solution. Considering a sparingly soluble salt AB in the solution, which dissociates into A plus and B minus ions, the equilibrium constant of this reaction is given by K equilibrium is equals to A activity of A plus into activity of B minus divided by activity of AB as our equation 41, where A of A plus and A of B minus and A of AB are the activities of A plus, B minus and AB respectively. The activity of a solid is arbitrarily taken to be unity. Therefore, equation 41 can be written as K equilibrium equals to A of A plus into A of B minus as our equation 42. The activity of the ions can be expressed in terms of their concentration as activity coefficients. That is, K equilibrium is equals to Ca plus into gamma A plus into Cb minus into gamma B minus, or K equilibrium is equals to Kc times gamma plus minus square as our equation 43, where Kc equals to C of A plus into C of B minus and gamma plus minus square is gamma plus into gamma minus as our equation 44. The equilibrium constant in this case is known by a special name and symbol, that is the true thermodynamic solubility product Ksp. Kc is the classical solubility product obtained by determining the actual concentrations of the ions in solution. Gamma plus minus can be determined from the extended Debye-Hückel law, that is Ksp equals to Kc into gamma plus minus square as our equation 45. Now looking at the determination of mean activity coefficient from electrochemical cell potential. The deviation of a solution from ideal behavior can be represented by means of activity coefficient gamma. The activity coefficient based upon molality m is defined as gamma equals to A by m, where A is the activity. This is our equation 46. An ideal solution is defined as one for which gamma is unity, but for a non-ideal solution it differs from unity. However, even for non-ideal solutions in the limit of zero ionic strength, the activities of ions are equal to their concentrations. The activity coefficients thus become unity in the limit of zero ionic strength. The ionic strength I is defined by the expression I equals to half summation mi/zi square as our equation 47, where mi is the molality of the ion and zi is the charge of the ions of type I. The Debye-Hückel limiting law predicts the mean ion activity coefficient gamma plus minus by the equation as log gamma plus minus equals to minus a z plus z minus into root I as our equation 16, where Zi and Z plus are the charges of anion and cation respectively. The constant A has the value of 0.509 at 25 degrees Celsius for aqueous solution. For a 1:1, that is a uni-univalent electrolytes, I is equals to M, and therefore we get log gamma plus minus equals to minus A root M as our equation 48. But the Debye-Hückel limiting law is valid for only very dilute solutions. In practice, deviations from the limiting law become appreciable in the concentration range from 0.005 to 0.01 molar. Guggenheim has shown that the mean activity coefficient obeys the following relation up to 0.2 molar concentrations for 1:1 electrolyte. This is given by equation 49 as log gamma plus minus equals to minus A root m divided by 1 plus root m plus Bm, where B is a function of interaction coefficients for each possible cation-anion combination and A equals to 0.5084 at 25 degrees Celsius. There are several methods for determination of activity coefficient. The measurement of electromotive force of a cell is one of the convenient methods. Consider here xm means that different molarities of HCl solution are used. The half reaction for the right electrode is Hg2Cl2 solid plus 2 electron gives 2 Hg liquid plus 2 Cl minus, and the half cell potential is E of Hg2Cl2 Hg equals to E naught minus RT by F ln A of Cl minus. This is our equation 50. At 25 degrees Celsius, E equals to 0.244 volts minus 0.05915 log ACl minus. This is our equation 51. The left side is the quinhydrone electrode. The electrode reaction is half Q plus H plus gives half QH2. The Nernst equation is E QQH2 equals to E naught minus RT by F ln A of QH2 raised to power 1 by 2 divided by A of Q raised to power 1 by 2 into A of H plus. This is our equation 52. In a saturated solution of quinhydrone, the concentrations of quinone and hydroquinone are equal and the activities are equal. Hence, AQH2 raised to power 1 by 2 equals to AQ raised to power 1 by 2. Thus, we have equation 53 as EQQH2 equals to E naught QQH2 minus 0.05915 log 1 by AH plus. The overall cell potential E is equals to E right minus E left, which can be further written as E naught minus 0.05915 log ACl minus AH plus as our equation 54, where E naught is E naught right minus E naught left. Furthermore, since we have ACl minus into AH plus equals to A plus minus square, and A plus minus is equals to gamma plus minus into M plus minus. For HCl, M plus minus is equals to M equals to M. Substituting A plus minus equals to gamma plus minus into M plus minus in equation 54, we have E equals to E naught minus 0.1183 log M minus 0.1183 log gamma plus minus, or E plus 0.1183 log M equals to E naught minus 0.1183 log gamma plus minus. This is our equation 55. This expression 55 provides with an equation to calculate mean activity coefficient using the cell potential. Now we shall summarize what we have learned in this module. The Debye-Hückel limiting law, which is valid with experimental values of the activity coefficient at extremely low electrolyte concentrations, while the law fails at high concentration. The Debye-Hückel theory was made applicable at higher concentration by introducing the concept of finite size of ions into the mathematical formulation. Hence, the Debye-Hückel law for finite sized ions is given as log gamma plus minus equals to minus A into Z plus Z minus into root I divided by 1 plus chi A. Mean activity coefficient can be determined experimentally from solubility product and from electrochemical potential of a cell.